the previous videos, we mentioned about the detailings of the structures. We have covered quite a lot, nearly every type of the structural element that you can see from the typical reinforced concrete structures. These include the beam, the slab, the columns, the foundations, the staircase, the gutters, as well as the architectural features. You know that the detailings is very important to the contractor, giving them an idea how the structures is being fabricated. It should be comprehensively illustrated, neatly presented, carrying all the essential informations required for the contractor to fabricate the member on the construction site. This video intends to give you some additional informations in terms of the typical sections as well as some issue with the reinforcement. In fact, we discussed about this previously. We also mentioned that we have typical size which are commonly used in the industry. Now we're going to talk a bit on the theoretical side. You know that the typical beam size for a good performance, you need to have a ratio of B over H of 0.3 to 0.6. The beam performs better with the smaller ratio as compared to the larger ratio. However, it cannot be too small, otherwise the beam will behave in a very slender mode where they can be concerned in terms of the lateral torsional buckling. And the ratio cannot be too big, as this is going to increase the weight of the member significantly, and this will lead to accelerations in terms of the increasing rate of the reinforcement bar required within the member. It is only when you do not have sufficient space within the ceiling that limits the effective height of the beam, then you go for the wide beam. Otherwise, try your best to keep within this range. And this table is actually worked out on basis of this ratio. If the B is 0.3 times of the ratio, that gives you a maximum height in this column. And if the B is considered 60% of the height, that means the minimum height it will be this. These are the typical width of the beams, as well as the applicable range of the beams. The more common one, it will be 150 times 450, which is in this category, or 230 times 600, which is at this category. The other size is also applicable. Whichever the size it is workable in the construction industry. Previously, you also mentioned about that 20% hanger bar, which you may refer to the video previously. The idea here is when you have the supports of the continuous member to be quite heavily reinforced, beware of this hanger bar. It cannot be less than 20% of the bigger of the areas of the reinforcement bar at the support. This represents the reinforcement bar at the support, and this represents the minimum amount of reinforcement bar as the hanger bar. Next, we also mention about equivalent reinforcement bar area, which you can reduce the unit of the reinforcement bar by increasing the size of the bar. We mentioned this verbally somewhere in the previous videos. Now it is demonstrated in the table for better understanding. The reason that sometimes you choose to reduce the numbers of the reinforcement bar, it is so that your beam sections have larger space, especially in the considerations of the minimum spacing between the reinforcement bar, which is meant for the pouring of the concrete and compactions of the concrete during the casting. What you see here, it is something interesting, that you have 3 units of T12. You can actually change it to 2 units of T16. You reduce 1 unit of the bar, but increase one size of the bar. Same goes to the other size, and you realize that By increasing the size of the bar, you are actually increasing the areas of the reinforcement bar. Probably this is the main reason that the standard size of the reinforcement bar that are available in the industry as designed by the manufacturer that have all this considered. Knowing this pattern, you can actually make a quick conversions even without the calculator, and you will know that if the member pass in this setup, after the conversions, it will definitely pass. Next, it will be the conversions of the shelling. This is for you to upgrade the size of the shelling. You may upgrade one size of the shelling while increasing the spacing by 75 mm. The amount of reinforcement, it will be more or less similar. And why do you need to upgrade the size of the shelling? Sometimes you find the shellings are too closely spaced. When the shellings is too closely spaced, the numbers of the shelling needs to be produced in the construction site increases significantly. Might as well you upgrade the size of the shelling. With a larger spacing between the shelling, the numbers of the shelling can be reduced. And this table represents the typical lap length as provided by a software. In fact, you can calculate your own lap length based on the equations provided by the Eurocode. In principles, there will be regions of good bond and there will be regions of poor bond. For the regions of the poor bond, for example, when the reinforcement bar is used as the top reinforcement bar, the typical lap length will be longer. And when the bar is used as the bottom bar, that means that will be the regions of good bond, better compactions of the concrete, good consolidations of the aggregate as a result of compactions. The lap length can be reduced. These are the typical lap length with respect to the size of the reinforcement bar. For you to adopt this value, it will be good that you do some cross-checking. Use your equations from the standards to verify those. And after all, it is meant for the education purpose. You need to know how those values are produced instead of observing what it is given by the software. In fact, you can create your own table here on basis of certain common conditions, and you do the calculations. Once you tabulate these tables, you don't have to calculate the required lap length every single time you need to do the lapping. Instead, you just refer to a table here for you to know what will be the minimum lapping length. In the case that you are lapping two reinforcement bars of different size, the lapping length will be in accordance to the smaller size. It is to allow the stress to effectively transfer from the bigger size to the smaller size reinforcement bar. Similar principles go for the design of the staircase. Actually, you can have a common design of the staircase, play around with the effective spans, as well as the dimensions. Use a spreadsheet for you to work out appropriate amount of reinforcement bar as the longitudinal reinforcement bar and as the transverse reinforcement bar. This one, it will be good of you if you really try to work out the table, and you just need to do one-time job. Design accordingly. Use the spreadsheet to generate all the possibilities, and then next time when you encounter the design for the staircase, you may straight away adopt the amount of reinforcement bar. If you choose to use the values as given here, you need to use it wisely. There could be errors in the calculations, as I also generate this from my own spreadsheet. The results are computed from the Excel spreadsheet for quick reference during the design stage. If you choose to use those values, you have to use it wisely at your own risk.